Welcome to question 8 of the 2018 Mathematical Methods Exam 1 for the Southern Hemisphere. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. So for question 8 we have let the function with the domain of all real numbers and a rule f of x equals x squared e to the power of kx, where k is a positive real constant. And we're asked to show that f dashed of x, the derivative, can be written as x e to the kx times kx plus 2. So to differentiate this, we can recognise two functions multiplied together, so we're going to need to use the product rule. And to apply the product rule, we can write u is the first function that's multiplied, so x squared, and v is the second function, so that's going to be e to the power of kx. And then we calculate du dx, which is simply 2x, and v dx, which is going to be equal to ke to the power of kx. And from our formula sheet, we know that the derivative d dx of a function u times v is equal to u times dv dx, and then we add on to that v times du dx. So therefore, for this question, f dashed of x, the derivative, is going to equal u times dv dx. So u is x squared times dv dx ke to the kx. That can be written as k x squared e to the kx. And then we add on to that v times du dx, which is e to the power of kx times 2x. So I'm going to write that as 2x e to the power of kx. Now to get it in the format that we want, we simply need to factorise. So the derivative's got a common factor of x e to the kx, so we can remove that out the front. So we have x e to the kx. And for this first term, there's kx that we would need to multiply it by to get the expanded form back to where it was. And for the second term, it's simply 2. And we can see that from what we were asked to show, that is the correct answer and what we were asked to show in this question. So from the examiner's report, we can see that 87% of students got that question correct, and that overall it was very well answered. For part B, we're asked to find the value of k for which the graphs of y equals f of x and y equals f dashed of x have only one point of intersection. So to start this problem, we're going to let both equations just equal each other. So we're going to have f of x is equal to f dashed of x. So that means that x squared e to the power of kx is going to equal, and the derivative we just found before was x e to the power of kx, and then in brackets kx plus 2. So to solve this, we're going to get everything onto one side of the equal sign so that it equals 0. So we would have x squared e to the power of kx, and then we would subtract away x e to the power of kx, bracket kx plus 2, and that will now equal 0. And then we're going to factor out a common factor of x e to the power of kx. So therefore, if we take that out, we get x e to the power of kx. And then left behind, we would need x and subtract kx plus 2. And that would equal 0. So that's the factorised form of the equation we're trying to solve. And now that it's factorised, we can use the Null Factor Law. So therefore, we would say that x could equal 0, e to the power of kx could equal 0, or finally x subtract kx minus 2 could equal 0. Now inspecting these possible solutions, x equals 0 is a valid solution. However, e to the power of kx equals 0 has no solution. So now our task is to find the value of k so that there's exactly one point of intersection. And from what we just found, we can see that x equals 0 is always going to be a solution. So there's always going to be a point of intersection at x equals 0. And then this equation can lead to a possible second solution. So if we want just one point of intersection, we just want it to be the x equals 0 solution. So therefore we need no solution for this second equation. So now our job is to find the value of k such that there's no solution to x minus kx minus 2 equals 0. So to do that, we're going to have x take kx has a common factor of x, so we can write that as x and then 1 take k, and then we're going to add the 2 across so that that equation equals 2. So therefore, x would equal 2 divided by 1 subtract k. And now inspecting this solution for x, we would see that if k equals 1, we get no solution. And that's because there's an asymptote at that point, if you think about that as a graph. So with that in mind, we know that x equals 0 is the only solution when k equals 1. So that is the answer to part B of this question. And now this was quite a challenging question, so just to explore that idea a little bit further, when we do have k equals 1, we simply would find the equation x take x subtract 2 is equal to 0, and the x subtract x would cancel, which would give negative 2 equals 0. However, that's nonsense in terms of our maths. We know that negative 2 can't equal 0, so that means that if k is equal to 1, there's no solution to that equation. So that's just a slightly different way of thinking about what we just discovered. So from the examiner's report, we can see that this was an exceptionally challenging question, with only 3% of students getting full marks for the question. And the examiner's report goes on to state that most students found the correct equation to solve. However, they often solve for k rather than x with the values that satisfied that equation. Few students realised that x equals 0 was the unique solution that we were after, and that the other part was finding a k value such that there was no second solution. Incorrect use of the null factor law and or the incorrect discriminant of the quadratic were main sources of error in this question. Next, we let g of x have the rule negative 2x e to the power of kx divided by k, and the diagram below shows a section of the graphs of f and g for x is greater than or equal to 0. Let A be the area of the region bounded by the curves of y equals f of x, y equals g of x, and the line x equals 2. And that's the shaded region shown in the diagram above. For part C, we're asked to write down a definite integral that gives the value of a. So we know that a is simply the area between two curves, so we're going to integrate between the lower bound of 0 and the upper bound of 2 of the upper function f of x minus the lower function, which is g of x with respect to x. So that is a suitable answer to part A of this question. From the examiner's report, we can see that the question was generally attempted well, with 63% of students getting full marks for the question, although students commonly did leave off the dx, which is an essential part of the integral, or found the sum of the integrals f and g rather than the difference of the integrals f and g, which was required for the area between those two curves. For part D, we're asked to use our result from part A or otherwise to find the value of k, such that A is equal to 16 on k, and A was the area between the two curves. So over to the right, we've got that diagram, and we know that the rule of f of x was x squared e to the power of kx, and g of x was negative 2x e to the kx on k, which means that A can be expressed as the integral between 0 and 2 of f of x, which is x squared e to the power of kx, and then we're going to subtract negative 2x e to the kx on k, and that will actually just change into plus 2x e to the power of kx on k, and that integral is with respect to x. Next, we're going to think back to our answer to part A, and we're going to set that up as a statement. And the statement is that the derivative d dx of x squared e to the power of kx was found to be, and I'm going to write it in expanded form rather than factorized form, even though that's what the show that question was asking us to do. And in expanded form, it is kx squared e to the power of kx plus 2x e to the power of kx. And now I'm thinking that this looks remarkably similar to this expression in the integrand of the integral that we need to evaluate. So this question's leading us towards what we'd call integration by recognition, and that's where if we integrate both sides of this equation, we can find an integral or the antiderivative of an expression that we couldn't do using the rules that we have on our formula sheet. Now, the only difference between the two orange lines that I've highlighted is a factor of k. So if I put a factor of 1 on k multiplying this integral, that will actually simplify to the blue integral above. But whatever I do to one side of this equation, I would have to do to the other side of the equation. So that is now still an equals statement. So where to next? Well, what we can say now is that a is equal to the integral between 0 and 2 of x squared e to the power of kx plus 2x e to the power of kx divided by k, and that's with respect to x. And now all of the work that we did above is to say that that integral is equivalent to this expression just here that I've put the red box around. So we can say that this is equal to 1 on k, but undoing the integral of a derivative just leaves x squared e to the power of kx, and because it's a definite integral we're going to put that in a square box, so it's going to be x squared e to the power of kx. We're going to evaluate that between the terminals of 0 and 2, which were on our original integral. And now we're getting much closer to our answer. So a we're going to let equal to 16 on k, which is written into the question. So therefore we're going to write 16 on k is equal to 1 on k, and then we're going to evaluate this antiderivative by substituting in the upper bound and then subtracting the lower bound substituted in. So putting 2 into that will give 2 squared is 4, and then we get e to the power of 2k, and then we subtract away the lower bound substituted in, but when we put 0 into there we just get 0 squared is 0 times anything is just going to be 0. So that's what we find the value of the definite integral to be equal to. And now multiplying both sides by k, we just get 16 is equal to 4e to the power of 2k. 4e to the power of 2k. And now dividing both sides of that equation by 4, we get 4 is equal to e to the power of 2k. So to find the value of k, we're going to need to write this as an equivalent log statement. So therefore we find that 2k is equal to log e of 4. And now to get k by itself from there, we simply divide by 2. So we get k is equal to 1/2 log e of 4. So that is the answer to part D of this question. So from the examiner's report we can see that 13% of students got full marks for this, and 41% of students made some progress getting 1 mark. A large number of students, 43%, got 0 marks for this question. And the examiner's report goes on to state that while students could equate their answer in Part C to 16 on K, many students did not use their result from Part A, which would have allowed them to evaluate that integral. Incorrect algebraic manipulation made progress difficult for some students along the way.